Hi, welcome. I'm Bijou Smith. My other handle is Achronon Master. And in this series I do simulations of NCEA exams, so New Zealand main high school standards. The reason I do these is to show you that, or to show students mainly, what the thinking could be like in an exam, because I do all my sort of inner thoughts to myself that I wouldn't normally do. That sometimes takes more time, right? It takes more time to do that. But still, since I'm an expert, and it should take me only as much time as it would a competent student. So if it takes me 1.5 hours to do this exam, I think students should be given, say, 2 hours to do these exams, so there are no stress, and you're not testing their performance under stress. You're testing their understanding of the curriculum and how to solve problems. That's how I regard these tutorials and videos. So they serve multiple purposes. You're welcome to use this as a library if you want to send them to the NZQA to show them that they need to instruct the schools to give students more time to sit these exams, so that there's no stress of time pressures, and also that it's really a test of the school, not a test of the student. I make some notes on these below in my description of these videos. Anyway, with that said, let's have a look at this sort of simulated exam here. These videos take a while to do because I'm just coming in at them raw and fresh, as if I was a student coming into the exam. That's the simulation aspect of it. So I'm not trying to do everything quick. I'm not trying to particularly teach anything. I'm just showing you what someone's thoughts in an exam might be under these circumstances. I put myself under a little bit of artificial time pressure because I want to try and finish it in say an hour or an hour and a half, so that I don't bore everyone. For students, you can use this as a resource. Just try the problem yourself. You can get these papers off the NZQA website. And pause the video anytime you think you can solve the problem, and just use this video if you like to as a check or as a bunch of hints. And if I make mistakes, that's not deliberate, but I keep them in these videos because I want to show you that it's easy for even an expert to make mistakes. I should really record all that as an intro one time. So waves paper. I know. I gotta say this. My daughter told me about this strategy of sitting exams where you don't do the achieve type of questions. You just go for the excellence, because you'll get an excellence endorsement anyway. But it's a risky thing, because then if you don't do well on the excellence questions, you've foregone the achieved questions. So I think that sort of overload, that cognitive load on students to sort of strategize about how to sit an exam is just ridiculous, and they should go away and they should be given ample time to do the exam. Another thing is, you'll notice if I make mistakes, I try to check or back check. I'll try to look try to find out where I made a mistake if I think I made a mistake, and that all takes a whole lot of time in an exam, a lot of time. And you just wonder why the qualifications people don't really appreciate that, or maybe they do, and they're just trying to be vicious to students, like teachers used to be in the old days, pre the new curriculum days, like since forever. But we don't have to follow tradition and do like Victorian school education. We can do better than that these days. Plus, all these questions are artificial and phony. Really, you want to get students using computers to solve problems and things like that these days. Use software and so forth. Anyway, that's enough of an intro. So we've got a node and an antinode. Which harmonic or overtone is shown in the above diagram? Well, for this thing, we've got fixed ends. The first harmonic is that. But even I don't know whether that's called the fundamental or the first harmonic. The fundamental is like the 0th. So the next one would be a standing wave that looks like this, right? So I call it the second harmonic. label those one node and one antinode. There is a node, and here is an antinode. The length of the guitar is so many meters, the frequency is so many hertz. We want the speed of sound through the string. So we're going to use the relationship between frequency, wavelength, and velocity. Just in case you forget that, it should be on your formula sheet, but lambda is an SI, units of your meters. Frequency would be hertz, which is 1/seconds. And so you see that lambda times frequency is going to give you a velocity. So check that. But I think a lot of things are in your formula sheets. What I do in these simulated exams is I kind of derive some of the formula stuff in the formula sheets, just as a sort of extra pedagogical thing, which makes these videos a bit longer than necessary. But I don't mind doing that. So anyway, what we've got is, so therefore V will be equal to 995 hertz is cycles per second. Okay, so the length of the guitar string is that. Now, this is the half wavelength that we've got here. So this is one wavelength, and so this will be 1.5 wavelengths. You get like 0 plus a half lambda, or n plus a half lambda from n equals 0 up to whatever higher frequency. These are the sets of wavelengths that you get. That's why n equals 0 is usually called the fundamental. If that's not correct, let me know in the comments. I don't do waves and stuff for professionally these days, so I forget the terminology. Shouldn't depend on the terminology. If you follow Feynman, you just say this is the this is the first fundamental, and then there's a bunch of others. You wouldn't bother getting into musical theory and worrying about what these words mean. You just say what the wavelength is. Anyway, yeah. Yeah, so that's equal to the length of the guitar string. Well, so this harmonic is 1.5 wavelengths, so 0.645 equals 1.5 wavelengths. So the wavelength is 0.645 over 1.5. So we've got 995 times 0.645 divided by 1.5. Go to your calculator. Round that up to 3 significant figures would be 428 meters per second. 3 significant figures. Okay. So they're playing the same note here. They hear beats of 5 hertz. Someone tightens their strings. Yeah, until they don't. Oh, okay, so the original frequency. So the beat frequency equals the difference of the two frequencies. That's 5. So that means 995 minus the Millet's frequency will be equal to 5 hertz. And so you can remove the absolute value signs. It'll be clearly F2 is 990. Well, hang on. She tightens her string. V equals F lambda, right? So she's changing the velocity to go faster in order to, and that'll make, if the wavelength is constant, because proportional to the length of the string, that'll mean the frequency will go up. So she had to be at a lower frequency, so 990, or you could say 200, but the tuning was to get V increased, hence frequency increased. Therefore, original frequency had to be the smaller one, because it had to go up to 995. Tightening the string is on the frequency of the note. So the tightening of the string increases the tension. And so if for a small displacement of the string like that, look at a small section of the string that's been shifted up like that, it's gonna whip back down. If the tension increases, it's gonna pull it back down further, so the wave is gonna travel faster. And a higher wave speed. And then finally you'd say for a fixed wavelength or fundamental, this will create a higher frequency. V proportional to the frequency. Next question, open pipe. Okay, so Jane's situation is like this. So there's some waves that could get set up like that. The boundary condition open at the end, free to move at the end, the air molecules, and the other one, clarinet. It looks like this, so it's nodes at one end and antinodes at the open end, plus or minus some sort of gap here. There's a little extra there you sometimes use for scholarship physics. It's like the effective length of the thing is usually a little bit bigger. Explain why I cannot produce a second harmonic. Okay, so the second harmonic is 1.5 wavelengths in plus a half for for n equals 0, 1, 2, right? Second harmonic. So you got the fundamental, you got the first harmonic, and then you got the second harmonic. Or you could have an open ends like this. So basically, three half wavelengths. 3 over 2, 2 plus 1 over 2. Yeah, so so this is the other one. So it could be an antinode to antinode, which means which is 3 half wavelengths. So I don't know how to explain this. Whether we have a node or an antinode. So start with a node at one end, start with an antinode at the other end. We either have a better way to explain it is for any musical instrument, I have a node at one end. So if it's a left is a node, that means the right end of the instrument is a hang on, sorry, forgot. This is 1 half wavelength, 2 half wavelengths, so 3 half wavelengths would be one more, right? 1, 2, 3, like that. 1, 2, and then the 2 halves. So right end is, so this is an antinode, this is a node. That means the right end is a node. If the left is an antinode, it means the right end also has to be an antinode. Therefore, you can't, the instrument like melees cannot produce a resonant second harmonic. Now they can produce the second harmonic, but it won't resonate for very long. Just be, they could force it, but it'll soon decay into one of the other proper normal modes of vibration. Okay, time for a cup of tea break. The fraction grading question. Well, let me do an extra aside pedagogically here. You remember the I think you get maybe what is it? You might get this formula in your formula sheet in Lambda, and it comes from the interference pattern from a screen with a whole lot of slits in it that are spaced D apart. Sorry, that's not the right D. It'd be between the two slits here, kind of the middle of the slits, which means that a wave front, little tiny wave front coming out of these will have a different this is the detector, a different path length to travel depending on which slit it goes through. And if we just make this reference here, this reference line, call it some angle. It's roughly the same angle from both slits, but the extra path length that is travelled, if you take a perpendicular from this one down here, you get this little bit here is the extra path length. So you get destructive interference. So so here's usually the pattern looks like a big node. We put the pattern in red here. Pattern will be bright and then dark and then bright and then dark and then bright, dark, bright, dark, bright, like that. So this is like a antinode, and in between you got nodes. Okay. Anyway, destructive interference would be a node. That would be when the wavelengths, when they hit the screen, have kind of gone some distance along here, like this, and the next one along would be out like 180 degrees out of phase with this one. So it'll go, the other one will go like that. So when they add together, you get a zero, flat zero. So if you started this one here, but you moved the other one along, how much did you move it along? You moved it along half a wavelength there, since from here to here is a whole wavelength. So this extra bit is a half wavelength. But that's the same for any multiple of n over 2. Sorry, any multiple of lambda over 2. But for constructive interference, it's sorry. So the path length, if we blow this region up here and look at that triangle between the two slits here, D, and we look at theta, the angle to the screen here, that would be that angle there, which turns out to be the same as that angle there, using a little bit of basic trigonometry. Then this path difference here, using some basic trigonometry again, will be this little delta, this side length here, will be sine of the angle. That's where we get the formula from. And so if the path difference is a multiple of half the wavelength, we get destructive interference. And here it's the path difference would be equal to a multiple of the whole wavelength. So that would be like you get one wave here, and the next wave is along here. So they add together. You just shifted the next wave all the way along here. All right. It means the sum of these two waves is going to be extra large, like that. Double the amplitude, so on. That's where that formula comes from. And so I think we're just going to put that in our heads, right? Whoops. And lambda for constructive interference. And that could be n equals 0 as well, since there could be a 0 path difference between the two. That would not correspond to d equals 0. It would correspond to sine of the angle equals 0. It's a straightforward direction. Anyway. Okay. If d increases and lambda is fixed, and the sine of the theta increases, so the fringes get further apart. So for each n, you'll have a larger angle. Sine theta will be equal to n lambda over d. Sorry, the decreases. What am I saying? Further apart. Oh, what's the opposite of that? Closer together. Mental picture in my head was the reverse of what the question was saying. Yeah. So two factors here. D, you increase D, you better, and the other side doesn't change. You better decrease the other factor proportionally. Okay, blue light. So D, D lines per meter here in the grating formula. Third bright dot, third order maxima. Okay, so we've got a pattern that looks like a pattern like that, and then 1, and then 2, and 3. 1, 2, 3. This is from the source in the grating here. So that's the n equals 0, n equals 1, n equals 2, n equals 3. Third bright dot and the central bright dot. Oh, that's the central. So 1, 2, 3. That's the third bright dot. The third bright fringe. So that's n equals. This applies n equals 3. And d sine theta equals n lambda. And so lambda equals d sine theta divided by 3, and frequency equals v over lambda, c over lambda. So it's 3.8. Oh, sorry, what is it? 2.977. I forget what they give you in the exam, but I think the speed of light they'll just give you is 3. Sometimes it might be 2.998 or something like that. It's meters per second. Anyway, that's divided by lambda, so we could multiply by 3 and divide by d sine theta, which would be 6 times 10 to the 5 times the sine of 54. And so all I have to do to remember is to make sure 54 times pi over 180 radians, because my calculator is in radians. So, yeah, let's have a look at that. Three times 10 to the 8 for the speed of light, times 3 for the order, 6 exponential 5 for the spacing, and sine of 54 times pi over 180. 1854 hertz. I think that's okay. Frequency of the frequency is equal to 1854. How many decimal places? 50 hertz. That's to 3 significant figures. We can drop the 4 because we don't have that much precision in our data. In a moment, I'm going to go check what the frequency of red light, frequency of blue light is. Wasn't sure if it should be that. Oh, wait a minute. Yeah. Oh no, D is wrong. Yeah, I knew that didn't look right. So there's a big mistake. I just knew that wasn't the right. That's my background knowledge. Of course, I was not taking into account the language here. D lines per meter. So the number of lines per unit length. Okay, so what we've got is a grating with like spacing. Okay, like this. Okay, and this is one line, and there's D here. So the lines per meter is going to be equal to 1 over D. And so D is going to be equal to 1 over the lines per meter, if you like, number of lines per meter. So that's going to be equal to 1 over 6. Well, let's just say 1 over 6 exponential 5. 1 over 6 times 10 to the 5. We don't have to calculate that. We just have to change our formula here to 1 divided by that thing. That's much better. Holy smoke. That's a huge number of hertz. I wonder if I plug that into Maximo, it'll tell me. I don't think. Nah, float. I don't want to calculate. Oh, sorry. What did I do there? I had a pi there. Right. Percentage for the pi there. 10 to the 14. That's much more reasonable. 6.67 times 10 to the power of 14 hertz cycles per second. Light cycles real fast. Useful to know the frequencies of visible light for these exams. Next is a white light, same grid spacing. Central antinode is white. Each order just produces a complete spectrum. Right, so in the grating equation, d sine theta equals n lambda for a given order in a fixed grating spacing d, different wavelengths will have constructive interference at different angles sine theta. So if the D is small enough, large, yeah, small enough. And this goes back to the first question that we answered. If D decreases, spread in theta between orders can be large enough that the constructive interference peaks from different wavelengths do not overlap. Excuse my messy writing because I'm writing with a tablet here. It's a bit slippery. It's hard. It's not like writing on paper. Anyway, from different wavelengths do not overlap. Hence, it is possible that all constructive interference peaks for the visible. Lambda can be seen as non-overlapping. I don't know whether it's 2 p's or 1 p. And complete spectrum. That is to say, a complete spectrum for visible light. Of lambda for visible at each order n. Do we have any more space? Yeah, but at the central node, all the lambda interfere at the single angle. Theta equals 0. Since it's the order is n equals 0. So so the spectrum is not separated. For the n equals 0 order here. Okay, while studying the effects of shining white light through the grating, carefully measures 28 degrees for violet. Then he measures this. Well, I forget, I'm not sure whether this is the same grating with the same D or not. But anyway, grating D is the same. Same order. Implies the N is the same. But we don't know what it is. But unknown. Could be N equals 1, 2, 3, I guess. And that means only if there's a change in angle, it can only be because of the change in wavelength. Right. So that means basic maths here. Whatever n is, lambda red equals d sine theta red, and the same n for lambda blue or violet equals d, same d sine, but the theta is different. Violet. This is 1, and that's equation 2. So we subtract 1 from 2. Sorry, yeah, 1 minus 2 implies n lambda red minus lambda violet. That's subtracting the left hand sides from each other and subtracting the right hand sides. Sine theta red minus sine theta violet. Calculate the wavelength of the red light. If that doesn't help you, there's another way of writing it, right? Because n over d is the same. So you could say, well, N over D is sine theta red. Better to do ratios, I think, here, right? Which equals sine theta violet. Lambda violet. Let's just say that, right? That kind of makes it a little simpler, because that means if we want to calculate the red light, I want to kind of eliminate the violet. So that means lambda violet. That's going to be, just rearrange this equation. It'll be lambda red times, you can do a reciprocal of those two equations if you like, if that makes it easier for you. Anyway, it'll be sine theta violet over sine theta red. So okay, so that means we can get rid of theta violet. So we've got lambda red. It's like a simultaneous equations problem if you were doing it more mathematically rigorously. Minus lambda violet, which is given by this thing now. So we just put that in there. Sine. Let's just do V and R for short. Equals 2.54 minus 7. Actually, when you think about this, we could check that frequency problem from before, right? Frequency is velocity over wavelength, so if it was 3 exponential 8 divided by 2.54 exponential negative 7. What? 1, 2, 3, 4, 5, 6, 7, 8, 12, 13, 14. Just, yep. That was a check on a previous question where we had a frequency of around 10 to the 14 hertz. Okay, that means lambda red, you can factorize that out. It's 1 minus the ratio of the sines. Okay, equals blah blah blah. So lambda red is equal to 2.54 times 10 to the negative 7 divided by 1 minus, bigger is right, 28.05. And 50.82. Now you should put your calculator in degree mode, perhaps, to make it easier for yourself, but you'll have to remember to switch it back to radians later, probably. So I'll have to put the conversion to radians in myself by hand. Seems reasonable. It's usually 633 nanometers, the orange red laser. So you expect a redder laser to be about 650. So that's 646. Significant figures.